So what we got going on here is we have a situation where we are seeing that water sticks to itself and that water sticks to other things, glass, cellulose, and now I'm going to try to explain to you what's going on with that. And it's knowledge we've been building on for a while now. So what do you know? You know that hydrogen atoms have one outie electron. So this one has one outie electron, this has one outie electron. They're not stable. Okay, they have to, they only have one energy level, so to be stable they can have no outie electrons or two. And so they can either gain one or lose one to become stable. Their partner in this is oxygen, which has 6 outie electrons. Remember, it also had, oxygen had 2 electrons in the first energy level. So oxygen has 8 protons, 8 electrons. It's neutral. And it needs 2 more, needs to gain 2 outie electrons to become stable. And we also know about oxygen, hopefully you remember that oxygen is a bully. Okay, so how do they reconcile their differences and work together? What's this whole thing about H2O? So if you think about it, each of these oxygens, each of these hydrogens, again saying the wrong word, has 1 outie electron, and there are 2 of them. And oxygen needs 2, so it's a perfect match. The thing is, hydrogen is not a bully and it's not a wimp, right? It can either gain or lose, so it's somewhere in between. It's going to give a good fight before it gives up its electrons, and in fact, it doesn't give them up completely. What we're going to end up with here is where hydrogen had 1 outie electron and 1 outie electron, and oxygen had 6, 1, 2, 3, 4, 5, 6. These 6 come from the oxygen, these 2 come from the hydrogens, but look what's going on here. The oxygen shares 1, the hydrogen shares 1, so now this hydrogen has access to 2 anyhow with that sharing, and this hydrogen has access to 2. So that allows stability for this hydrogen, stability for this hydrogen, and stability for the oxygen. But it requires them to share their outie electrons. Okay, but they don't do it equally, right? We've got a bully here, and we've got 2 things that aren't wimps, and so they're not shared equally. As you can see in this hydrogen doesn't have equal access, right? The hydrogen's way out here, the nucleus, and the electrons are way over here. And the same for this one. So what we have is like a proton out here, a proton out here. So this end of the molecule has a positive charge. This end of the molecule, the oxygen end, has a negative charge, right? There's a surplus of electrons. There are more electrons than protons, so this end is negative. And these 2 parts, which we can average by putting it here, this end is positive. So what we have is called a polar molecule. It has a negative pole, a negative end, and a positive pole, a positive end. Okay, and so where that gets really interesting is when there's something else around that's polar, right? Like another water molecule. Because, bang, they're going to stick together. If they can, they're going to stick together. They're going to, so we've got a couple of different kinds of bonds here, and I don't want to confuse you. So if you got that, and that's all you can stand, you can punch out. But if you're playing with a sharp pencil, then I want to tell you that the oxygen and the hydrogen are held together by sharing. And that's called a covalent. We could call it a co-outie electron bond, right? Because they're sharing them. So that's a covalent bond that holds the oxygens and the hydrogen together. And then this is one of those weird science names. They call these 2 molecules sticking together a hydrogen bond. I have no idea why. But if this water molecule were to stick to glass, that would be a hydrogen bond. Or, just from the positive to a negative, because glass is more polar than water. Or cellulose is more polar than water. And so the negative end is going to stick to a positive pole of the water, of a water, or of a glass, or of a cellulose. And I think that's probably enough for this. Hopefully this makes sense. Okay, thanks.